Good morning. Today we'll see whether this today we'll look after some delay programs in 8051. How to calculate a delay of 1 second, 1 millisecond, 10 milliseconds at all. And before understanding this, here each and every instruction, each and every mnemonic in 8051 will have some machine cycles to complete its operation. For example, microcontroller clock frequency of microcontroller is 12 megahertz, right? So not 12 megahertz, but what is uh, actually it is 11.595 megahertz something, right? Megahertz, but 11.75 megahertz, 595 megahertz, but approximately for our convenience, take it as 12 megahertz. Example, if the microcontroller clock frequency is 12 megahertz, frequency is 12, then what is time? 1 by frequency, correct? 1 by 12 mega 12 megahertz. So therefore it comes under 1 microsecond. So you see, not 1 microsecond, 1 by 12 into 10 power 6 seconds. The time period of machine cycles here, to complete a one machine cycle in 8051 or any processor, machine cycle is nothing but a execution of time required to complete uh, uh, one instruction completely. So here any instruction, either we written in assembly language, the first is a opcode, operation code. So here first of all, three operation has to carry out while executing the instruction. The first one is opcode fetch. By this, controller knows what kind of operation has to perform. And next, once opcode fetch is completed, uh, fetching fetching what is a machine cycle is? Machine cycle consists of steps that computer processor executes whenever it receives a machine language instruction, and it is the most basic CPU operation. And the modern CPU are able to perform millions of machine cycles per second. The cycle consisting of three standard steps. Those are fetch, decode, and execute. So in the first cycle, it fetches the information and decodes, and then after that execution. And all these three operations are very important in a machine cycle. To complete one instruction in 8051, 12 machine cycles are required. 12 machine cycles are required. So therefore, the time required for 12 machine cycle, but time required for one machine cycle is equal to 12 divided by time period of one state. So even this 12 machine cycles group of T states, the group of T states here, it may require for fetch cycle. Fetch cycle requires a 3 T states, and like that. Decode requires uh, 4 T states, and execute requires 4, 3 T states, six, six states, like that. So all these three combinations is considered as one machine cycle. Machine cycle. And my total are 12 machine cycles. I'm not saying exactly 3 and 4 6 states, but it have some states based on the instruction. So therefore, see how to calculate a delay program. So here I loaded this or not register with at 0 FFH, means 255. FFH is a decimal equivalent of 255. And decrement or not, and jump on no zero. Here, decrement or not, jump on no zero to here. Like that, this or not will decrements by 255 times. So therefore, this particular instruction, number of machine cycle required to execute this jump on no decrement and jump on no zero instruction, we require two machine cycles. This we need to know, otherwise they will give for our calculations. And for a exam point of view, we need to remember these machine cycles. And next, this instruction requires only one machine cycle, and this return instruction is also return instruction needs two machine cycles. Why? Because whenever return instruction is there, the lost program counter main address is pushed onto the stock, so we need to pop it. So that's why we require two machine cycle here. Now, say a number of times executed. Say this particular instruction is loaded only once, so therefore one time is executed. But this particular instruction is executed 255 times, decimal times, and this particular instruction, return instruction, executed only once. So therefore, number of machine cycles multiplied by total number of times executed, that gives a total number of machine cycles. And here, this is a two machine cycle is required to perform this decrement and jump on no zero instruction. But how many times is it is executing? 255 times. So therefore, 255 multiplied by 2, that is 510 decimal value. Again, here return instruction requires a two machine cycles, but how many times it executed in a program? One time. So therefore, 2 multiplied by 1, 2 multiplied by 1, 2. So therefore, total number of machine cycles is 530 decimal value. So time period of one state, 1 by 12 into 10 power 6 seconds. But one machine cycle, 12 states. How many? 1 microsecond. Time required to complete a one machine cycle is 1 microsecond. So therefore, for execution of total this delay program, he requires how many machine cycles are there? Total 513 machine cycles are there. Multiplied by the time, how much time required to complete a one machine cycle? 1 microsecond. So therefore, total 513 microseconds. This particular program, particular delay program generates 513 microseconds of delay. And we'll see the next another delay program where here the nested delay will be there. So initially delay program. So move again, a or not is loaded with 0 FFH. Next, another register R1 is loaded with again 0 FFH 255 number. Next, decrement Pj and Z R1 comma loop 1 itself. Here itself it jumps. Next, Dj and Z Dj and Z are not up, move to up in this position. Now this is a delay program. Now we'll see the how many number of cycles required, machine cycle required to complete this instruction is one machine cycle is required. For this also one machine cycle is required. For this particular sorry, so here we are jumping this up, where this instruction is included in blue. Okay, machine cycle is one. So this is a machine cycle. How many machine cycle required? Here is 2. Here also how many machine cycle required is 2 to execute this instruction. And next return instruction is there. Here also we require 2 machine cycles. Then how many times it is executes? This is only one time it executes. And this is, see here, this particular instruction is inside the loop, so therefore this particular instruction is executed at 255 times. And whereas this particular instruction is executed, say 255 multiplied by 255 times. Why? Because here R0 is loaded with 0 FH, and this particular R1, this particular instruction is loop itself continuous. Decrement R0, if it is not equal to 0, jump again. Decrement R1, if it is not equal to 0, jump again. Like this, total this count which should become 0, then only next instruction will be executed. And next instruction R0 is decremented and it's not equal to 0, so for them jump again. Again R1 is equal to 0 FFH. Well, R1 again executes 255 times. So therefore 255 multiplied by 255 times this particular instruction will execute. Whereas this instruction executes only 255 times. Why? Because it's outdoor loop. And this instruction executes only once. So therefore, total number of machine cycle required is 1 multiplied by how many times it executes. This is 1 machine cycle is required to in this one, and this is 255 machine cycles are required. And here 255 into 255, 1330050. This many machine cycles are required to complete this particular instruction in a given program. Here are 255 machine cycles. Here 2 machine cycles are required. The total machine cycles are 130818. This is a decimal value. So decimal value. And as we know that the time required to complete a one machine cycle, time required to complete a one machine cycle is time required to complete one machine cycle is 1 microsecond. Right? Therefore, how much time required to complete 1,30,818 machine cycle? So therefore, so the delay produced by above program is equal to time required for one machine cycle multiplied by total number of machine cycles. Total number of machine cycles, so which is equal to 1 microsecond multiplied by 130818, which is equal to 130818 microseconds. Okay, the delay period of above subroutine can be increased by increasing the number of loops. By changing the initial value loaded into the register, we can able to change the delay period of time delay subroutines. Time delay subroutines. So this is all about delay, how to calculate a delay programs. So here next video will look after how to write and what here to generate 1 milliseconds, what kind of what value we need to load in R0 and R1 registers or any other registers, and what value which delivers 1 milliseconds. So that can be calculated with the help of T-mod. 8051 has on mod registers. It has timers and counters. 2 16-bit timers will be there, where we can load the count value on the 8051. It generates a required amount of delay. So therefore, in next video, I'll record how to generate a delay with the help of T-mod registers, timer registers of 8051. Thank you so much. We'll stop here.